Okay, we're going to look at some problems for partial differential equations, specifically looking at the wave equation. So looking at a question from 1997. We have a wave equation, d squared u dx squared is equal to 1 over c squared d squared u dt squared. And we're given some boundary conditions and some initial conditions. So the boundary conditions are simply that the position u at x is equal to 0 and x is equal to L is going to be equal to 0. So this tells us that this is a wave equation being solved on a string of length L, and we're holding the ends of that string constant. We're also given some initial conditions here. We're told about the velocity at time t is equal to 0 and the displacement at time t is equal to 0, but we're not going to use those until later on. So the first thing we're going to do, and the first thing we do in every kind of question like this, is to make our separation of variables assumption. So what we're going to do is we're going to let u of x and t be written as the product of a piece that deals with the x part and a piece that deals with the t part, so f of x times g of t. Now that's an assumption, of course. So that means that we can transform our partial derivatives, so the derivative of u with respect to x is only going to affect f of x, so that'll become ordinary derivative of f with respect to x. It doesn't do anything to g of t. And I'm going to introduce the notation that the derivative of f is f prime. So f of x is just a function of one variable, so writing it as a prime there clearly means that I'm taking the derivative with respect to its argument. I can find the second derivative with respect to x as well, so that becomes a second derivative with respect to x there, and I get 2 primes. I can do the same for the derivative with respect to t, so u 2 derivatives with respect to t isn't going to affect f of x, but it will give me 2 derivatives with respect to time of g. And again, I'm going to use the notation that prime for g of t means derivative with respect to t. Okay, that means now that my partial differential equation, which was uxx is equal to 1 over c squared utt, is going to become f double prime x g of t is equal to 1 over c squared f of x g double prime t. Okay, now what I can do is I can separate this equation. I can bring all the terms involving x to the left-hand side and everything else to the right-hand side. So dividing by f of x and multiplying by dividing by f of x on the left, dividing by g of t on the right. So I've gathered all the x's on the left, all the t's on the right, and I've also kept that factor of c squared on the right-hand side, and that's just for convenience. But you notice now that I have an expression here that is x on the left, function of x only, and it's a function of t only on the right. So this is our usual argument that if I've got a function of x equal to a function of t, the only way those two functions can be equal to one another is if they're both equal to the constant function. So k is a constant. So this then allows me to write 2 separate ordinary differential equations. F double dash x over f of x is equal to k, which implies that f double dash x minus k times f of x is equal to 0. And I've got g double dash t over g of t, let's not forget that factor of c squared, is also equal to k, the same k. So I can rewrite this equation as g double dash t minus is equal to k over c squared g of t. So these are our two equations, an equation for the time-dependent part, g of t, and an equation for the spatial part, the part that depends upon x. And we're going to deal with the part that depends upon x first. Now to do that, we're going to have to know something about the boundary conditions for this ordinary differential equations, the boundary conditions on f of x. And so we're going to take a look at our boundary conditions on u of x and t and turn them into boundary conditions for f of x. So the boundary conditions we saw were u at x is equal to 0 was equal to 0, and u at x is equal to L for all values of t was equal to 0. Now how do I turn those into boundary conditions for f of x? Well, we know that u can be written as f of the x part, and x is equal to 0, times g of the t part. Now if this is equal to 0, I've got something times something is equal to 0. F of 0 times g of t is equal to 0. So one of these two things has to be 0. Now if g of t was equal to 0 for every value of t, you'd see that my solution would be 0 for all time. So the only way I can solve this and get a non-trivial solution is if f of 0 is equal to 0. That is, my function f is 0 when x is equal to 0. So that's one boundary condition for f of x. I could do the same thing at x is equal to L. Again, u can be written as a function f of x times g of t. If I evaluate that at x is equal to L, I get something times something is equal to 0. So one of these two somethings must be equal to 0. It can't be g of t, so it must be f of L. So now I have my two boundary conditions, and I'm going to use these to whittle down all the different possible values of k, so I get my non-trivial solutions. Now we need to consider the different possibilities for k. Let's write down the equation we're solving again. So we're solving the equation f double dash x minus k f of x is equal to 0. And we don't know what the value k is. So we're going to consider the different possibilities. The first possibility is that k is a positive number. So the way I'm going to represent that is by setting k is equal to p squared, which will automatically be a positive number for p not equal to 0. So we'll just look at p greater than 0. Now the reason I'm writing it as k is equal to p squared is because that's going to make my calculation a little bit easier later on. So this is really just a mathematical trick for convenience. So when I do that, I get f double dash minus p squared, f is equal to 0. That's a second order ordinary differential equation with, and it's homogeneous, there's no right hand side. So what I can do is I can assume a solution of the form e to the lambda times x. That means that every derivative of f becomes a power of lambda, which means that my characteristic equation is lambda squared minus p squared is equal to 0, which means that lambda is equal to plus or minus p. So that gives me the following solution. f of x is equal to a times e to the px plus b e to the minus px. So a and b are constants of integration. Now, to figure out what those constants are, I'm going to have to use my boundary conditions. So using the boundary conditions at x is equal to 0, using the boundary conditions at x is equal to 0 and at x is equal to L, I have that f at x is equal to 0 has to be equal to 0. Right? So let's substitute x is equal to 0 into this expression. I get a times e to the 0 is 1, plus b times e to the 0 is 1. So I get a plus b is equal to 0, which means that b is equal to minus a. So it eliminates b in terms of a. Let's use the other boundary condition. At x is equal to L, this is also equal to 0. I'm going to substitute in x is equal to L into this expression, so I get a e to the p times L plus b e to the minus p times L. Now I've already found out that b is equal to minus a, so I can make use of that right away. So I have an expression now in terms of a, p, and L. Now once again I've got something times something is equal to 0. So that implies that one of those has to be 0. So either a is equal to 0 or e to the pl minus e to the minus pl is equal to 0. So let's consider the first of those possibilities. A is equal to 0. Now notice that we found that f of x was equal to a e to the px plus b e to the minus px. But if a is equal to 0, it implies that b is equal to 0, so this whole expression here would be equal to 0. So if a is equal to 0 and b is equal to 0, f of x is equal to 0 for every possible value of x, which means that this is just giving me the trivial solution that u is equal to 0 everywhere. So we're looking for a non-trivial solution. That leaves us with this possibility. E to the pl minus e to the minus pl is equal to 0. So this is a condition on p and l. Now I could pull out a factor of e to the pl here. Or rather, I can pull that e to the minus pl over to the other side and then multiply both sides by e to the pl. That'll give me e to the 2 times pl is equal to 1. Now you notice that I've got e to the something is equal to 1. And the only way I can have e to the something is equal to 1 is if that something is equal to 0. Now L can't be 0, obviously 2 isn't 0, so P has to be equal to 0. But we already assumed that P was not equal to 0. In fact, that P was a positive number. We assume that because we're actually going to consider the possibility of K is equal to 0 specifically later on. So we assume that P was not equal to 0, so we've got a contradiction. So what this shows is that when K is a positive number, there are no non-trivial solutions. Let's move to the next possibility. Let's look at K is equal to 0. So this is case 2. K is equal to 0. So what does my differential equation become? It's f double dash x is equal to 0. I can immediately solve that by just integrating to give me f of x is equal to ax plus b. Again, I've got two unknown constants that I need to fix using my boundary conditions. So at x is equal to 0, f has to be equal to 0. So let's substitute x is equal to 0 into my solution here. I get a times 0 plus b. So that's going to give me b is equal to 0. Let's look at the other boundary condition at x is equal to L. I also know that f is 0 there. Substituting that into my expression here, I'm going to get a times L. I know that b is equal to 0, so I don't have to include that. Now L is not going to be 0. L is the length of my string. I don't have a 0 length string. So that implies that a is equal to 0. So once again, I get a solution that's 0 for every value of x. Which means that this is just the trivial solution. So we've seen that the possibility when k is a positive number or when k is equal to 0 only gives me trivial solutions. Let's hope that the last case gives me a non-trivial solution. So the last case was when k is a negative number. So I'm going to use that trick of setting this as equal to minus p squared, which is strictly negative. And again, I'm assuming here that p is not equal to 0, and it just for to be specific, I'm going to say that p is a positive number. And that again is mostly for mathematical convenience. So my differential equation now is going to become f double dash of x plus p squared f of x equal to 0. You notice this is a second order homogeneous differential equation. I can assume a solution of the form f of x is equal to e to the lambda x, which means that every derivative turns into a power of lambda, which means my characteristic equation is lambda squared plus p squared is equal to 0, which has complex solutions, imaginary solutions. Lambda is equal to plus or minus I times p. So that means that my solution f of x is the sum of cosines and sines. Where again I have unknown constants a and b, which I'm going to fix using the boundary conditions. So the first boundary condition was at x is equal to 0, f is equal to 0, which is going to give me a times cosine of 0 is 1, plus b times sine of 0 is 0, so it gives me a. So that implies that a is just equal to 0. Okay, so now I'm left with just f of x is equal to b sine px. So what about the boundary condition at x is equal to L? A is equal to 0, so I don't have to worry about this part. What about b? Well, I have b sine p times L. So once again, I've got something times something is equal to 0, which means that one of those things has to be 0. So either b is equal to 0, or sine of pl is equal to 0. Now the first possibility, b is equal to 0, and a is equal to 0, is just going to give me f of x is equal to 0. So again, it gives me the trivial solution. So what about the other possibility, sine of pl is equal to 0? Well, I know that the sine of an integer multiple of pi is equal to 0. So I can say sine of n pi is equal to 0 for n is equal to 1, 2, and so on. And you notice if I compare those expressions that I can conclude that p times l must be an integer multiple of pi. Notice that I didn't include the possibility that n was equal to 0 there. because that would have given me p is equal to 0, and I've already excluded the possibility that p is equal to 0. But p is equal to n pi over L works perfectly fine as long as n is an integer greater than 0. So what I found now is that there are infinitely many solutions to this. F of x is equal to b sine p times x, where p is equal to any integer multiple of pi over L, and we're multiplying that by x. Now you notice that works for any value of n equals to 1, 2, 3, 4, or whatever. And since any of those are possible solutions, I get infinitely many different solutions. So I'm going to put a little subscript n in front of f to indicate that this is the solution for that particular value of n. And I'm going to put a little subscript n beside b to indicate that that's the coefficient corresponding to the solution for that particular value of n. Okay, so now I found f of x for all possible values of n. Now I'm ready to go back and actually solve for g of t. Let's remind ourselves what the equation was. We had g double prime of t is equal to scroll back up here. So I see a little mistake that I made here. Let's correct that. The equation we started off with was this equation, 1 over c squared g double prime over g is equal to k. If I multiply up by that c squared, I get g double prime is equal to kc squared. So here's the equation that we're going to solve. Now the thing to remember about this is that the value of k hasn't changed. It has to be the same for both f of x and g of t. So we have g double prime of t is equal to k c squared g of t. And we saw that k was equal to minus p squared. So we have minus p squared c squared g of t, where again we saw that p was equal to n pi over L. So we fixed k to be a negative number, and then we figured out what that negative number should be in terms of n. So now I can use this to solve for g of t. Notice now that g of t is a second order homogeneous differential equation, which means that I can assume a solution of the form e to the mt. So that means that every derivative of g with respect to t is going to give me a power of m. So my characteristic equation is going to become m squared, so the two derivatives of g is equal to minus all this stuff. So minus n squared pi squared c squared over L squared. So again, that's just writing down the characteristic equation, assuming that g of t goes like an exponential. So this also has imaginary solutions. So m is equal to plus or minus I times the square root of all that stuff, which means that g of t also looks like sines and cosines. So g of t will be c times cosine. I'm not going to use the same coefficients as f of x. So cosine n pi c over L times t plus d times m, so that was n pi c over L times t. Now you notice here that this is the solution, g of t, for this particular value of n, and we know that n can take values 1, 2, 3, and so on. So I'm going to put a little subscripts here, g sub n, c sub n, and d sub n, because those functions and those coefficients will be different depending on what n is. Now, to figure out what c and d are, I'm going to have to use my initial conditions. So the first of those was that the derivative of u with respect to t at time t is equal to 0 was equal to 0. So basically, the rate of change in time of the displacement at time 0 is equal to 0. Now, what does that mean in terms of f and g? Well, remember that u was equal to f times x, f of x times g of t. A derivative with respect to t is only going to affect g, and we're evaluating at time t is equal to 0. So you notice here that I've got something times something is equal to 0. One of those two things has to be 0. It can't be f of x, because that just tells me that my solution is 0 everywhere. So it means that the initial condition for g is g prime at t is equal to 0 is equal to 0. So just like the boundary conditions, which told us what the values of f were at x is equal to 0 and x is equal to L, the initial conditions tell us something about the value of g and g prime at time t is equal to 0. So let's make use of this. I have a solution, g of t. I know that the derivative of that at time t is equal to 0 must be 0. So let's take the derivative of g. And I'm going to do this for all values of n, not just any particular value. So just taking derivatives here is fairly straightforward. Derivative of cosine gives me minus cn, and then I have to pull out those terms appearing inside the brackets there, n pi c over L times sine. And the derivative of sine is going to give me n pi c over L times cosine. That's the derivative. Now let's calculate what that is at time t is equal to 0. So substituting in t is equal to 0, it's going to give me sine of 0, which is 0, and cosine of 0, which is 1. So this is going to give me dn n pi c over L, and that all has to be equal to 0. Now we know that c can't be 0, the speed of the wave can't be 0, n can't be 0, so this is implying that dn is equal to 0. So it's killing off one of those coefficients that we picked up. Alright, so where does that leave us now? We found that g of n at time, all times, was equal to cn cosine n pi c over L times t. And I found that f of n of x is equal to an unknown coefficient bn sine n pi x over L. So I can actually put this together now to get u of x and t. And this is going to be the solution for a particular value of n. So it's going to be fn of x, gn of t. So we see that's going to be bn sine n pi x over L times cn cosine n pi c t over L. And you see that I've got two coefficients here now, bn and cn, but they appear in the combination b times c. So I can actually introduce one last coefficient, let's call it en. And now I have a single coefficient for every n. where here E is just Bn times Cn. So here's my solution for this particular value of n. Of course, the most general possible solution will be the superposition of all of those. So my full solution will be something like this. It'll be u of x and t is the sum for all possible values of n, integer values of n from 1 to infinity, of en sine n pi x over L cosine n pi c t over L. And you see that I have infinitely many unknown coefficients En. And once again, I'm going to use an initial condition to figure out what those coefficients have to be. The initial condition that I'm left with is the initial displacement, which was given by u of x at time t is equal to 0. It was given by a function f of x, which was 2 sine 4 pi x over L. So let's put t is equal to 0 into my expression for u of x and t, and then match up coefficients. So t is equal to 0 is going to give me cosine of 0, which is 1. So I get en sine n pi x over L. Let's write out the first couple of terms there. I've got e1 sine when n is equal to 1, so I got pi x over L. e2 sine 2 pi x over L plus e3 sine 3 pi x over L, and so on. e4 e5 and there are infinitely many terms. Now I know that this expression has to be equal to the initial condition at time t is equal to 0. So that was given by 2 sine 4 pi x over L. So you see that I have an expression here on the left that involves lots of different signs, an expression on the right that involves only one of the signs. So now I can start matching up coefficients. And you see that there's no sine pi x over L, there's no sine 2 pi x over L, 3 pi x over L, or 5 pi x over L appearing on my right hand side. That means that all of these terms must be equal to 0, every single one of them. The only one that's not equal to 0 can be the sine 4 pi x over L, because that's the only term that has a corresponding term on my right hand side. So I can immediately read off what the value of En has to be. En will be 0 for all n not equal to 4, and for n is equal to 4, it'll be equal to 2. So again, every single one of these e's has to be 0 because there's no corresponding coefficient on the right hand side. The only one left is e4, and that's got to be equal to 2. So I finally have my full solution. U of x and t will be given by the sum over n, but all of them are 0 except for 4. So I'm going to have 2 sine 4 pi x over L times cosine 4 pi ct over L. And this is the solution to my wave equation that matches those boundary conditions and initial conditions.